Good morning, Astronomy 1010. Welcome to the second part of Lecture 7. Subtitle, The Professor is Still Sick, but the Show Must Go On. I'm feeling a little better than Monday when I gave you a live lecture, but you guys were asked to watch a pre-recording of the sixth lab on spectroscopy. And hopefully you guys got through that. Did you guys use colored pencils to make the spectroscopic lines? Okay, that's great. I hope you had something to work with there. I'll see what it looks like when I grade your papers. I haven't done, you used a PDF editor. Okay, Ryan, did you use colored lines when you put those spectroscopic lines in? That sounds good, Ryan. I love it, okay? I haven't done any grading in days, actually weeks, I guess, if you count spring break. At some point, I'll do my job, I promise. Just sit tight and give me a little time and I'll get to that. Please try to stay on top of these labs and homeworks. I know it gets exhausting as we get towards the second half of the semester here, but continuing to get those labs and homeworks in will guarantee that your grade comes out good, no matter how ugly the tests get. In our last lecture, we learned about different types of spectra and the art of spectroscopy. We also learned about the electromagnetic spectrum. So let's see, to start off, what you guys know. What has more energy, a gamma ray or a radio photon?
Gamma ray?
Gamma ray. They're higher energy than radio waves. Which has a longer wavelength?
Photon?
Well, they're both photons. Gamma rays.
Well, the radio one?
The radio photon has a longer wavelength. Yeah. Some radio photons can be as long as a school bus or a jet airplane. They're quite long. Different astronomers work in different areas of the electromagnetic spectrum, and it allows them to see different parts of things like galaxies or nebulae. There are astronomers who just work in the domain of radio telescopes. There are some that work entirely in the optical. A telescope like this that you might buy at a store is an optical telescope. It works at visible wavelengths that your eye can see. So in other words, you look and you see the moon. What range of wavelengths does this run from? Do you know the numbers in nanometers? See, your capacity for me to teach you new things depends a little bit on your ability to remember the old things that I've taught you, because they stack on top of each other, kind of like a Jenga puzzle, right? So I'm just wondering if you guys know what the range of wavelengths are for visible light.
400 to 6 something?
Almost. What were you going to say, Kim? Or Kim, did you have an idea?
400 to 700 nanometers.
Very good. That's the Roy G or the VIB-GeOR spectrum, right? That's the visible regime. Nicely done, Kim. Austin, you were close. I'll give you a honorable mention. Okay. All right. Let's take a look at some different concepts from last time. The things I want to do today are talk a little bit about black bodies and spectra, and then I want to move on to develop a couple of key formulas. Your book has a chapter dedicated to different types of telescopes. In theory, it would be super cool to do an entire lecture sequence on telescopes, but I kind of don't have time because I want to get to the moons of Jupiter and things like that. So I have to pick and choose what I have time for. Let me start by having you look at a couple of slides. Actually, one more question that I need you guys to answer. What are the three different types of spectra that we find in nature when we take light and we break that light apart with either a prism or with a diffraction grating? Can you remind the class what those different types of spectra are?
Is it continuous, emission line, and absorption?
Beautiful, Jenna. You're right on top of it. You're doing crap. Okay, and let's see if we could guess what type of spectra would come from different types of things. So, well, Let's just start by looking at some pictures of them. I think I want to do that before I get into the notes today. So you will remember that during our last lecture, I started off with a hydrogen atom. And I told you that the orbits of the electrons within a hydrogen atom are quantized. Electrons can only orbit on pre-proscribed tracks. If you want to know why, well, that's a bigger question. It's got to do with quantum mechanics and the fact that nature is choppy and pixelated at some fundamental scale. For some reason, electrons can have stable orbits here and here and here, but they are not allowed to make a stable orbit in between. Each of these orbits has a different distance from the proton, and each of these orbits has a different energy. We sometimes call the orbits energy levels. And this, for instance, is the energy level diagram of a simple hydrogen atom, showing you the different energies that an electron can have. When the electron jumps between these orbits, things happen with light. The most important one is the process of emission, where an electron drops from a high orbit to a low orbit and emits a photon of hyper unique wavelength and frequency. In fact, that's the principle behind one of these lasers here that you could use either for pointing on the board, or I have these lasers for astronomy purposes because they're quite bright, or they're quite luminous, and I can actually point them onto the sky and point out stars to people. It's kind of fun. Maybe if one day COVID is finally over, you guys can come visit the Margaret Jacobi Observatory at CCRI, and I can give you a constellation tour and show you some fun things through the telescope. That would be a pretty nice time for everyone. This laser is created by getting electrons excited up to a very unique energy state and getting millions and billions and trillions of them to all drop at the same time. So I get bazillions of green photons of exact wavelength 532. This laser is monochromatic. It is one hyper-specific color of green based on the wavelength 532. Usually lasers, of course, have a cool electric neon 80s color that is kind of cool to look at. One thing I was kind of getting to towards the end of class is that there are many different emission lines even within a single atom. For instance, you would have seen during your lab that hydrogen has 3 unique lines. Hydrogen alpha is a red emission line, hydrogen beta is a blue emission line, and hydrogen gamma is a purple. I believe in the recording that I showed you guys, we had trouble seeing the hydrogen gamma line, correct? Is that right? You remember that, Kim? Yeah, I got to get a new hydrogen tube there because it's getting a little burned out. One of the things I sort of got to at the end of class, but I didn't feel great about, was just really trying to drive home the point that different atoms on the periodic table, they each have a unique emission line spectrum. Unfortunately, in this picture that I'm showing you, the order of the colors has been reversed to Roy G. Biv with red on the left. So hopefully that won't screw you up too much. You'll notice that hydrogen has these 3 red, blue, purple lines. Neon, you might remember from our lab, has tons of red emission lines. That one was probably really annoying to do. Helium has a red line, a yellow line, a couple of greens, a couple of blues. Sodium is famous for having only one set of emission lines in the visible regime. It's known as the sodium doublet, and it's 2 extremely bright yellow lines which are right next to each other. If you've ever been cooking mac and cheese on the stove or some salty pasta, and the salt water has bubbled over the pot and hit the gas flame, you might notice that when the salt water hits the gas flame, you see a little burst of yellow. Have you guys ever seen that before? I know sometimes when I cook pasta that it goes over, you see a little burst of yellow. You're actually seeing the sodium doublet from the sodium, salt is sodium chloride. So you're seeing those sodium atoms hit the gas flame, and that little burst of yellow is from this really bright sodium doublet. So you've actually seen these emission lines during everyday activities, but just not recognized what they are. In fact, because each atom has a unique set of emission lines, spectroscopy is the art of taking light, breaking it apart into different spectra, and then based on which emission lines you see, you can identify elements within that substance. And this is famously how we discovered all of the different atoms in the periodic table. Literally, the man who invented the Bunsen burner, what's his name? Edward Bunsen? I forget what his first name is, but he is, oh, is someone chiming in here? If I start a fire today trying to experiment, would insurance cover that? Austin, I cannot condone that as your public representative teacher here. I suppose if you had a spectrograph, you would learn. Actually, okay, you know what, Austin? You want to goof around? Let's go there.
Let's goof off.
Let's go there. What type of spectrum would a fire produce? If I analyze this with a spectrograph, what type of spectrum does this represent? You've got three options. Choose one.
Okay, can you name the three options? Wait, emission?
you're
It'd be
supposed
emission. Emission.
Why would you say it's emission?
Because it's like, to me, I look at that and the word emitting means to like produce
look,
and output.
Could you just use
We had the
Kirchhoff's
same
law?
problem last year, Professor.
Yeah, could we use Kirchhoff's laws? That's what you're supposed to. You are supposed to refer to the greats, okay? Refer to the greats, refer to Kirchhoff to tell you what type of spectrum this will produce.
Okay.
Okay, can I show
Hold on,
him now?
Jennifer. Yes, you can.
Do we have some class participation here?
Yes.
Can anyone help? Oh,
Done.
oh shit, what is that? Is that a little puppy?
Yeah.
His name is
Don't try to
Paquito.
wiggle your way out of this question by showing us a cute little puppy. Who the hell is that guy?
His
Damn,
name. Wait, where Paquito?
no
stop
wonder you
saying-
haven't been coming to class. Who is that guy?
Yeah, it's her fault too. His name's Nachito Paquito.
Cheeto Paquito, huh? Holy shit. Nakito Chep.
He's so cute.
It's cute. It's really damn cute. Okay. This isn't letting you off the hook though. You got to be able to identify the spectrum. I could ask you this on a
All
test, okay?
So Kirchhoff has three laws, right? There's continuous, absorption, and emission.
Correct.
Okay. So
And you were saying this,
that lighter is a low density hot gas, and I'm seeing it against a cooler line or cooler background, so it would emit an emission line, right?
yeah. Yes,
Okay.
I would have thought the same thing when I was taking Astronomy 101, Austin. Austin, you did everything right. You applied Kirchhoff's laws correctly, and you got the wrong answer.
What the fuck? What is that?
Let's find out, okay? Let's see if I can hold this up to the camera and find out what we got here, okay? So I'm gonna see if I can get us here. What type of spectrum is it?
Continuous.
Yeah, Kim. I've got to say that I'm sympathizing with Austin here. The first time I asked myself this question, I tried to apply Kirchhoff's laws, and I thought the answer would be emission because a hot, thin gas produces an emission line spectrum. But lo and behold, when we analyze the spectrum of a flame, it's blackbody radiation. It's a continuous spectrum. Does anyone want to take a guess why? I don't expect you to know why, but the problem is
Because
that
it's hot.
Well, it's hot. That's one of the conditions. The problem is Kirchhoff's laws are kind of hand wavy. They don't tell you just how dense a thing is supposed to be. In fact, it's quite unfortunate that Kirchhoff used the term solid because it's perfectly possible to create blackbody radiation from not solid objects. The problem is the air density in this room is still much, much too dense for emission line radiation to be produced. In order to get emission lines, you literally have to have a gas that is so low density that it's almost like a vacuum. That's why we had to generate emission lines by putting gases in these tubes here. The density of gas in this tube is hundreds and hundreds of times lower than the density of air. And that ensures that the atoms will have a very large separation between each other, and they won't interfere with each other when the electrons are jumping up and down. As you condense and pack a material closer together, what ends up happening is the matter gets so close that the electrons can not only jump within their own atoms, but they can also leap over to neighboring atoms. And those energy gaps are different, and they start producing so many different trillions of lines that it just fills up like a rainbow continuum. So in other words, if you look at a fire, even though it seems it's made of the gas of air, is still blackbody radiation because air is too dense to create emission lines. In that sense, Kirchhoff kind of tricked us a bit, because it would have been nicer if he said that. In fact, let's start with this as our note for the day, okay? So let's make this be our today's starting notes. Let's talk about blackbody radiation. I killed this marker, so it's time for a freshie. It's unfortunate. All right. So if we want to talk about blackbody radiation, we have to talk about something like this. According to Kirchhoff, he called it a hot, dense solid. But as I just demonstrated to the class, solid is really not the appropriate term. A hot, dense thingy would have been more appropriate, because sometimes black bodies can be produced by gases. One of the reasons that lesson that we had there was so important is next week we're going to be studying the awesomeness that is the sun. And you will discover that the surface of the sun, the so-called photosphere, which you can see in this picture here, the surface of the sun is made of a gas that is 10 to 100 times lower density than the air you're breathing in your house right now. And yet the surface of the sun, even though it's less dense than the air in the room, is still dense enough to create blackbody radiation. So when you look up at the yellow disk of the sun on the sky, you are getting a complete Roy G. Biv spectrum. Of course, if you paid close attention to the end of last class's lab, you'll remember that the sun actually produces an absorption line spectrum, but we'll talk more about that later. So what do we know about blackbody radiation? Blackbody radiation usually produces white light. It's not always white, but it's usually whitish. And that white light, when broken apart, produces a rainbow. Here's another issue. Another issue is that blackbody light depends on one property alone. Once you have something dense enough to be a blackbody, it depends upon the temperature of the thingy. It does not depend on the substance, the atom, the molecule, the chemical. Everything glows the same just based on temperature. Depends on temperature, not substance or chemical composition. I have a phrase that I associate in my mind with black bodies, and it goes a little something like this. I glow because I'm hot. That's the idea behind a black body. Black bodies glow because they're hot. If I had to show you like the most perfect idealized description of a black body. Sometimes I like to find this picture, this kind of goofy picture on the internet. So work with me here, of a steel ingot in a forge. And there's just a crummy looking picture here that I think really captures the essence of what a black body looks like. Hold on a second. This picture here, I don't know why, but for some reason I love this picture of a oh wow, that's really small. Click to enlarge. All right, you guys can see that, right? All right. So what you see is this piece of metal. It's kind of like rectangular. Actually, they call it a parallelepiped, if you really want to know. A three-dimensional rectangle is called a parallelepiped. So it's a parallelepiped of glowing metal. It's dense, it's hot, it's giving off this kind of orangey yellow light. And I assure you, if you held your spectroscope up to that glowing object, you would see a complete rainbow. So, what do we notice about black bodies, about things that glow with white light? Well, maybe one of the most ideal examples, besides that glowing ingot that I just showed you, would be for us to consider a typical tungsten light bulb, okay? So I want to bounce back and forth between slide 17. Actually, you know what? We need to do a kids break because I don't think we've done the inverse square law yet. I'm remembering this. Okay, we have to have a little digression before I can get into blackbody radiation. When we talk about glowing objects that produce big beams of light, we have to analyze light in a slightly different way than we've done so far. Up to now, we've kind of talked about photons, individual bits of light, and we've talked about their wavelength and their frequency and their energy. But things are a little bit different when you analyze something like a light bulb. So let's consider a glowing light bulb for a second. Function F527. The thing that actually produces the light inside of the light bulb is a glowing piece of metal called tungsten. So while the wires in your house might be made of copper, when you actually want to produce light from hot glowing metal, you produce it with tungsten for two reasons. One, it has a very high resistivity, so the electrons passing through the metal really crack into the atoms and cause the electrons to jump. The second is that tungsten has a very, very high melting point. And that means that you can get it very hot and make it glow without actually vaporizing the metal into a gas, okay? Tungsten is actually a pure element on the periodic table. I'm sure you've never noticed it before unless you've taken many chemistry courses. The element tungsten has the symbol W. It's a sort of uncommon metal. It's atom number 74, okay? I want you to notice that it's 1, 2, 3, 4, 5, 6 atoms down and 1, 2, 3, 4, 5, 6 atoms across. I have a super cool slide called the Spectra periodic table of the elements, and it shows you every single element in the periodic table and the spectra that's associated with it. Tungsten is 1, 2, 3, 4, 6 down, 1, 2, 3, 4, 6 across. It's this atom here. You'll notice that tungsten, has a unique emission line spectrum. It's got some blue emission lines, a couple of greens, an orange one. But of course, when you heat up tungsten in your light bulb, it glows like a black body. You guys should know why now. Why does the tungsten filament glow like a black body and not produce that spectrum? Jenna, can you answer that?
Is it due to the density?
That's right. It's in a dense solid metal state. The only way you could get tungsten to produce that type of spectrum, Jenna, is if I could vaporize it into a gas and put it in a low density tube like we saw in our labs. Okay, good. You did great. Just what I wanted to hear. Let's go ahead and analyze how a light bulb works together. We have to have a talk here.
Professor,
Yeah.
in theory, you could find new elements by finding new emission lines.
That's how they do it. In fact, because most of the atoms that are found in nature have already been discovered by scientists, there is a cottage industry of physicists who smash really massive atoms together, like plutonium and uranium and atom smashers, and see if for a short period of time they can temporarily create some big unnatural element. And they have all stupid names for them, like californicium or, lawrencium or something like that. These atoms usually decay in something like 10 to the minus 8 seconds. But while they're there, they look. Sorry, Austin?
I said those scientists are a bunch of dicks, it seems like.
Well, I
They
don't
just
know. I
want
mean,
their name on an element. It's
if you
not
can
even
get paid
doing
200K a year to smash atoms together, that sure beats working, right?
it. Yeah, I guess.
I mean, what do you want to do for work? You want to make a burger? You want to make pasta? Or you want to smash atoms together? It's all noble depending on your interests. Personally, I'd rather smash atoms together, but that's me, right? Okay.
Professor, could you find other elements on the other planets?
So we're going to eventually talk about that, but it turns out that it's not as willy-nilly random as you might think, because most of the gas in outer space that forms stars and planets has roughly the same composition. In other words, when we find other planets and other stars, they're forming from big clouds of hydrogen and helium gas with trace amounts of other heavy elements. Now, yes, you end up having quite a variety of planets even within our own solar system. For instance, the surface of Pluto is covered in frozen nitrogen. In our own planet, we have an atmosphere made of nitrogen and oxygen, and I'll get into why later. So there is some diversity, but for the most part, if you look at the terrestrial planets in our solar system, like Mercury, Venus, Earth, and Mars, they're actually made of the same basic recipe, which is a core of iron and nickel and an outer crust of silicate rock. So it's not as, for instance, I could see why you might think, oh, maybe I'll look out and I'll find a star that's made out of bubble gum, or maybe one that's made of plutonium or something. But it just doesn't work like that because of the relative abundance of the metals that we find in space. But you're not ready to have that discussion yet. You need to have this discussion first. Okay, let's talk about macroscopic descriptions of light. A macroscopic light analysis. So let's start with a simple Edison tungsten light bulb. You've got your filament here, okay? Actually, that's kind of a bad drawing. I'm going to try that one more time. Let's see if I can do that a little better. Okay. Still not great, but we'll deal with it. And this light bulb is glowing white black body light in all directions. And when you turn this light on, photons begin to shine and stream out of the bulb in all directions. You could talk about the energy of a single photon, but it doesn't make sense to talk about the energy coming out of the bulb because energy is constantly flowing from the bulb. Instead, what you might do is you might try to ask how much energy flows out of the bulb in some unit of time, like a day or an hour or even a second. And they actually have tools that can do this for you. You've probably never seen anything like this before, but there's this device called an integrating sphere. You can actually plug your light bulb into the socket, and this is a light sensitive meter that surrounds the light bulb. You close it up, turn on the light bulb, and you start to measure the energy of light coming out of it. It turns out that since energy is flowing out every second, you really want to measure something called the power, which is a measure of the energy flow. So power in physics is defined as energy per unit time. We might have actually talked about this during our homework. The units of energy in the MKS system are joules. MKS units of time are the second. So for the units of power, we define a watt to be 1 joule per second. Power or wattage can be measured anywhere there is energy flow. You can measure the wattage of a light bulb. You can measure the wattage of a guitar amplifier or a hair dryer, or even your own body, which, as you remember from your homework last week or 2 weeks ago, requires 2,500 calories per day. And that itself is a type of power. When we're referring to light, we tend to not use the term power. We use instead the term luminosity. Luminosity is the power of light. It's measured in the same units, which is watts. 1 watt is 1 joule per second. Put a box around that. That seems important to me. One last thing about luminosity that I think is worth mentioning. For any particular object, like say, for instance, this light bulb, the wattage or the light output of an object like a light bulb is always the same. It remains fixed. If this is a, how many watts is this? This is one of those fancy LED light bulbs from IKEA. So this is only 11 watts. If this is an 11 watt bulb, it's 11 watts whether it's right in front of my eye or at the other side of the room. That's telling me how much light comes out of the sphere in all 360-degree directions. So let's make this note that I think is important. Luminosity is a fixed property of a glowing object. In other words, the luminosity does not depend upon how close or far away you are from the object. This is all new, right? Jenna, we haven't put this into your notes before, correct? All right. No, all right. Lemon ginger tea. Love being sick. All right. May I erase? Okay. Let's play a little game together for a second to make sure you understand the things that I just talked about. I just told you that the luminosity of a particular object is a fixed property. Let's talk about the sun for a second. The sun has a luminosity of 4 times 10 to the 26 watts. That is a crazy amount of light output. It's hard to understand just what that means. You know, in science fiction, there's this concept that in the future, when humans are more technologically advanced, we might be able to get to a point where we could surround our entire sun with a light gathering integrating sphere. It's known as a Dyson Sphere, after the science fiction writer Freeman Dyson, who came up with the concept. We would take this giant solar panel bag, we'll cover the sun with it, and we'll absorb every single photon that it emits. And like some kind of a cosmic tick, we'll suck all the energy off of our star. That would be insane. Let's suppose you could do that. Let's suppose you could surround the sun with a Dyson sphere. And let's say you could collect all the photons emanated from the sun for just 1 second. So 1 second of total sunlight. Can you guys answer me this question? How much energy would I get? And I want you to see, think hard about this and see if you can figure that out. If I could collect all the energy emanated from the sun for 1 second, how much energy would I get?
Wouldn't it be its total luminosity, the 4 to the 4 times 10 to the 26th watt?
You were almost right, but you said it.
But it would be in joules. 4 times 6 is 26 joules.
Jenna understands me. This wasn't a question about conceptual math or anything. This was a question about units. Was that Paul G that I heard in the background there?
Yep, that's me.
We're collecting it over 1 second, right? So Jenna gave me the answer I wanted to hear. If the sun emits 4 times 10 to the 26 joules per second, then in 1 second, you end up with a total energy of 4 times 10 to the 26 joules. The purpose of that exercise was twofold. One, to demonstrate the difference between energy and luminosity. The second was to say, holy shit, there is a lot of energy in the sun. For instance, consider the entire United States. In 1 year, the entire United States energy consumption is a grand total of 10 to the power of 20 joules, suggesting that if you could collect 1 second of light from the sun, you would have more energy than the entire United States needs. Think about that. 1 second of total sunlight, you can power all the toasters and the microwaves and the Nintendos and the street lamps and all of that stuff. But for how long? Anyone want to try that question? If I could capture that 4 times 10 to the 26 joules, how long would I be able to power the US energy needs if we require 1 times 10 to the 20 joules per year? This sounds like a job for dimensional analysis. And for that, I'd like to turn over to our resident dimensional analysis expert, Ian. Ian has been dying to participate all day, but he hasn't really gotten the chance to butt in because so many people are talking. So Ian, I'm just going to give you a moment here to really steal the spotlight and show us how this is done.
You're killing me.
So look, just take this from dimensional analysis. You got 4 times 10 to the 26 joules.
Yeah.
That's how much energy the sun produces. And then you have 1 times 10 to the 20 joules per year. I want to know how long. What are the units going to be for that answer?
Joules per year?
No, joules per year is a power. I want to know how long. When I measure how long something takes, give me
okay. So are we doing it in years then?
Sure. I want to know how many years I could power the US based on that energy consumption. This is a power, and that's a luminosity.
Yeah.
What are you going to do dimensional analysis wise to take joules and joules per year and just turn it into a year? How would that work?
This is the stage 2, isn't it?
That is correct.
Okay.
I'm testing you on your ability. Very good. I'm testing you on your ability to do stage 2 dimensional analysis. So
Okay.
place the units in the slot until it works out.
So joules on top of both?
That will give you joules squared.
No, yeah, okay. So joules on top on the left, on the bottom on the right. Yeah, that would make sense.
Okay, and then what?
And then year in the other places.
Then you have all units cancel out and you have nothing.
You're right. Okay.
Keep going. You'll get there. Just keep trying.
Well, I mean, I guess we can put year on the bottom of the left one because we have one that's already.
You want to end up with units of per year. If joules cancel out and years on the bottom, you're going to have units of per year. 1 over year. So that doesn't make sense.
So would you put year on top then?
I guess so. If I want an answer in years, The only way I can end up with it is if years go on top somewhere. Okay, now tell me where to put. So now you figured it out. You figured out how to arrange the units properly. Now tell me where the numbers go.
Okay. 4 times 10 to the 26th would go on the left. Top
Top or
left.
bottom?
Top.
Fine. And how about over here?
I think you would put 1 year on top and then 1 times 10 to the 20th with the joules.
Good. Now you're doing level 2. Now, let's not stop there. Let's continue to do this in our head. What is 4 divided by 1?
4.
Okay. Now we do times 10, and you have to subtract the powers. So how do you?
Right. So that's just 6 to
And
the
what
6th.
are my units?
Years.
So I ask you again, Ian, if I could capture 1 second of total sunlight from the sun using a Dyson sphere, how long could I power all the Nintendos in the United States?
4 million years.
4 million years of free electricity from just 1 stupid second of sunlight.
Yeah.
Think about that. Isn't that insane?
Yeah.
I don't get it, man. Why haven't we done this? Why haven't I captured all 4 times 10 to the 26 of those joules in 1 second? For, I was hoping, a really obvious reason to everyone.
Oh, I didn't know if you wanted us to answer just, technological capabilities.
It's not just that. You're over here, Ian, on Earth, and you can capture this much light, whatever little cone of light splashes on the Earth. Most of those photons emitted by the sun are blasting off into other directions in space so that aliens can see our sun as a little star twinkling on their sky, right? All of those photons blasting off the sun are just getting totally wasted to the vacuum of space. The point of that, Ian, is that you don't capture all the luminosity that an object emits because it emits luminosity in all directions. You capture a tiny fragment of that light known as the brightness. The brightness of a light source is how much of a little cone of light or a little 3D rectangle of light what would you call this? A pyramid of light or something. Let's call it a cone. It's how much of a cone of light you capture at some distance away from the object. And this is a different property of light. It's known as the brightness. Let's talk about that. I need to erase here, okay? Okay. Let's talk about brightness. Brightness is defined as luminosity per unit area. And it can be kind of modular. It can show up in a bunch of different ways. One way to think about brightness is to imagine having a light bulb, and then there's some small cone of light that's coming off of it. And the area is the area that the light is being splashed over. Okay, so there's your area. Usually brightness depends on how far away you are from the object, okay? It depends upon the distance. And the units of brightness are the MKS units of luminosity in area. It's watts per square meter. I can talk about the brightness at the surface of a star, like you see in this picture. Like I could say, we know the sun has some luminosity, so I could imagine drawing a square meter panel on the surface of the sun and asking how many watts are flowing right through that square meter. Another way that I can look at brightness is I could think about looking at a star from some distance away And here I'd like to show you this picture. Imagine that you were capturing some amount of sunlight at Earth's distance at 1 AU. Basically, the 4 times 10 to the 26 watts would be spread out over this huge sphere, and the brightness would be how many watts were flowing through a 1 square meter panel. One of the cool things about spheres is we know some of their properties. Like, it is known from geometry that the surface area of a sphere is 4 times pi times its radius squared. So if you count up all the square panels over this sphere, 4 pi r squared, you can calculate the brightness at any distance by doing luminosity divided by 4 pi. Sometimes you write r squared, sometimes you write d squared. This is a legendary and classic formula known as the inverse square law. Let's take some notes on that. I'm erasing. All right, introducing a really critical formula. The inverse square law. And it has 2 different versions. One is brightness is luminosity over 4 pi r squared. The other version is brightness is luminosity over 4 pi d squared. In fact, both versions are the same formula, the inverse square law. But sometimes you want to use it to get the brightness at the surface of a star or planet. Then you might want to use the radius of the star. Other times you want to know how bright the object is on your sky. This tells you the brightness of a star in your sky, given that the object is some distance d away. Let's try an example. Here's an example. Find the brightness of the sun at Earth's distance. And here we're going to imagine that we go up above the atmosphere of Earth, because the atmosphere of Earth absorbs and scatters some of the sunlight, so we lose some of it. So I'm instead saying, suppose you were like an astronaut on a spacewalk, okay? Suppose you held up a 1 square meter panel towards the sun. So imagine that this dude who's up in outer space, by the way, I should mention, wow, what a crappy image. I hate how Google makes images small now. They're trying to encourage you to look at the website, but it's just totally freaking lame. Oh, I really hate that. Okay. So imagine you're this guy. And by the way, I should mention that a square meter is actually a pretty big panel. This meter is even hard to hold up in my field of view here. Here's 1 meter tall and 1 meter squared. Notice that a square meter is actually pretty close to the area of this board here, okay? So this dry erase board that I borrowed from CCRI is approximately 1 square meter across. That's a pretty good reference. Do you guys know how to do this problem? What would I do? Which version of the formula do I want?
You want the one with distance, because it's
Correct.
not the.
And what will I, so we know the luminosity of the sun is 4 times 10 to the 26 watts. What will I use for the distance, Ian?
Would you use 1 AU?
Correct, but here's the problem. Our units need to be in watts per square meter, not watts per square AU. So,
Sorry, let me find the conversion. I think it's 150 million.
but it's 150 million kilometers.
Yeah, Yeah, right.
Once again, I don't want watts per square kilometer. I want watts per square meter.
So that would just become 150 billion
Very good. If
meters.
you multiply that by 1,000 meters per kilometer, you get 150 billion meters. Okay, if you can do that fast in your head, then I don't need to explain that so carefully. Let's go ahead and try the calculation. So we have the brightness is equal to 4 times 10 to the 26 watts over 4 pi times 150 billion meters squared. I want everyone to try punching that into your calculator because it's really easy to screw this up. Go ahead and give that a whack. Why don't you just give me a number? Why don't you, I'd like to get to the point where you guys can just round it and tell me what the answer is, with units, of course. Well,
So
I'm adjusting the angle of my camera here. I want the screen like this, and I want the camera like that.
So you could put it as 1,400 watts per meter squared.
Excellent. Did anyone have trouble getting that? You better talk to me now, because you're certainly going to have trouble on the test. Anyone have trouble getting that number? You got it too, Kim? I guess you're cool like that, huh? Let's just say you're not cool like that, because I know somebody's not. All right, we did 4 exp 26 divide by 4 divide by pi divide by 150 billion squared equals, okay? Nori, you better have your calculator today. Do you have your calculator today? What are you doing to me, man?
I'm not home today, so I have not my stuff, so.
And you couldn't bring this with you, anticipating that you'd have to take the most awesome class in the world and you'd want to be prepared for that class?
Yeah, it was a spontaneous leave.
Okay, all right. You know what? Fine.
Sorry.
Life's complex. I get it. Could you, this doesn't weigh much, right? Do you think you could keep this in your purse from now on? You could even use it to tip at restaurants and things. You'll know like how much the tip is. I don't know,
Okay.
like do something, you know? All right. I want you guys training with me, all right? This is training time. Okay, I got to move on here. Nicely done. So you've now calculated a brightness. Now it's time for us to talk about black bodies. We can talk about black bodies in terms of brightness as well. There are 2 laws associated with black bodies that can help us further understand them and will help with our homework today as well. I want you to consider what happens when you take a hot, dense object and you put it into the fire, okay? And you heat it up. All right. I have an iron poker, and when it's cold, it does not glow. This is a dense solid. I place it into a fire. It begins to heat up, and first the metal glows dull orange, then red hot, and then white hot. And that's about as hot as you can get it in your household fireplace. If, however, you could continue to heat this metal up, in like with a bellows or in a blast furnace, eventually at some temperature, the metal would actually stop looking white and it would start to glow like a pale blue color. And it would probably look pretty awesome. Ryan, I just saw your chat about would it block out the sun. I'm not sure what that was in reference to, but if you can phrase your question again, I'll try to answer it. Okay,
think it was
so I want
about
to talk.
Sorry, I remember seeing that message. It was during the Dyson Sphere. You were asking why we
Oh,
couldn't do
yeah.
that.
The Dyson Sphere would block out the sun, so you couldn't actually do it outside of, you'd have to do it outside the orbit of Earth. Otherwise, every plant and thing would die. So we need energy from the sun. Another idea would be to leave a hole in the Dyson Sphere so that only Earth gets the light and we steal it from all the other planets. We'd have to think about the ethics of a Dyson Sphere. But anyways, assuming there's no other living organisms in the solar system but us, it might not be unethical to do it. Okay, so let's talk about black bodies.
Professor, do you think there are other living organisms?
Well, that's going to be one of the fun journeys we take in this class. In the past, there could have been, it's very plausible, there could have been living organisms on Mars, but as Mars's atmosphere died off, they're all probably since gone. There's probably no more living organisms on Mars unless there's some very strange extremophiles buried in the permafrost. However, there is a moon of Jupiter known as Europa, and we have strong evidence to believe that Europa has a giant sub-ice ocean that surpasses the total volume of all of Earth's oceans. Considering that life most likely originated in our ocean and can survive in very cold temperatures, if there's an ocean full of salty goodness that's been brewing for 5 billion years around Jupiter, it is totally within the realm of possibility that there are living organisms under the ice. And at some point, we are going to make a mission to go there and drill through it and look for signs of that. So it's totally possible, Austin, that there are places in our solar system where life could exist. There's still a lot of unexplored territory. So don't feel too defeated. There's still a possibility.
We'll find tons of water bears on there.
Yeah, we could find some tardigrades in there, right? Or worse, we could bring them there, and then they could fester and multiply and create a giant tardigrade planet, right? All right. So as I heat a black body, I get two effects that are interesting and worth talking about. And the first effect is that more temperature means you will produce more light outputted. So you guys will notice that when I heat up an iron poker, if you forget about the color for a second, the warmer and warmer it gets, the brighter and the brighter the metal will glow. Imagine that I was to take a small square patch of that glowing object and ask about its brightness. I would discover something called the Stefan Boltzmann Law. The brightness emitted from that tiny patch is a magical number. It's called the Stefan Boltzmann constant, but we usually use the Greek letter sigma to represent it. Sigma times temperature to the fourth, where sigma is just a number. 6 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth. It's got some kind of crazy units, and it's known as the Stefan Boltzmann constant. There's a lot of physics going on there, but you guys don't have to worry too much about that right now. Write that down while I adjust the temperature. Let's talk about the second effect. The second effect that you couldn't help but notice is as you heat up a black body, the color it emits changes. It goes from sort of not glowing to a red color to a white color and eventually to a blue color. Now, here we have to talk a little more particular about what's going on. Let's say that when you heated up a black body, you looked intensely at the rainbow that it was producing, and you asked yourself, how much light is emitted for each color? In other words, let me try to explain this here. Imagine that you took some kind of a light scanner and you scanned along this chart from, from purple to blue, or to indigo to blue to green to yellow to orange to red. And you asked yourself at each wavelength, how much wattage would I be getting, or how many watts per square meter? In other words, you try to measure the brightness of the rainbow color-wise. And the question you're trying to ask is, are any of these colors brighter than the others, or do they all have the same brightness? If you perform this experiment, you discover that not all wavelengths of rainbow light are emitted equally, and it kind of depends upon temperature. Forget about these other curves for a second. I want you to focus on the 4000 Kelvin curve, which is sort of like the curve for a white light bulb, like a tungsten filament light bulb that you would plug into your lamp at home. You would discover that all colors of light are emitted by a black body, but that the amount of light that you received, so on this axis, you're measuring the intensity or the quantity of light, probably in watts per meter squared. And on this wavelength, in this axis, you're measuring the wavelength. You'll notice that the visible spectrum is here, but we've also included the infrared spectrum and the radio spectrum, and ultraviolet would be over here. Black bodies produce all wavelengths of the electromagnetic spectrum, but they do not produce all wavelengths equally. There is always one color or one wavelength which is brighter than all the rest, and that's the peak wavelength of emission. This observation is described like this. More temperature equals bluer light. And it's described by an equation known as Wein's law. Or I guess if you pronounced it in German, it would be Wien's law, right? And it tells us that lambda max, the peak wavelength emitted, is a random number, 3 million nanometer kelvins, divided by the temperature T. Let's write those formulas down because they're going to be really important for today's homework. Have you guys got that? Sample problem versus, let's take one more set of notes. I want to introduce that drawing that I just showed you. It's known as a blackbody spectrum profile or something like this. It has a bunch of different names, and it's a famous plot. I want you guys to sketch it with me. On the y-axis, we're going to plot the brightness of my black body in units of watts per meter squared. On this axis, we're going to plot the wavelength in nanometers. We're going to include Roy G. Biv, okay? So we'll have purple light at 400 nanometers. We'll have green at 500 nanometers. We'll have red at 700 nanometers. But we're also going to include the other parts of the electromagnetic spectrum. Infrared, radio, UV, X-rays, and gamma rays. Now, suppose I heat up a black body, even this air is black body, and I look at that rainbow and I ask myself, which color is it emitting the most of? Is there more red coming out, or yellow, or blue? It's sometimes very difficult to tell with your naked eye. I wonder if I could do, I bet I could do a little demo on this. Okay, look, I have a great demo in mind, but I don't have time to set it up. I'm going to run out of time if I do that. Let me ask a different question. Suppose when you looked at the rainbow emitted by a black body, that all colors were emitted equally. What would the curve look like if all the colors had the same brightness or intensity?
A straight line.
That's right. It would just be a horizontal line. When you actually analyze the problem and you make observations, you discover that it's not a same line, that black bodies never emit all colors equally. They always emit colors in a particular pattern called a black body spectrum profile. And it kind of looks like a bell curve, but it's lopsided. It goes up, it hits a peak, and then it has a wide slope on the other end. There is always one wavelength that is brighter than the others. It's called lambda max. And the two takeaways that I would notice from this is black bodies emit all wavelengths of the EM spectrum. That's kind of observation point number one. This is why it's white light. This is why it's a rainbow. But not all wavelengths are emitted equally. This lambda max is described by Wein's law. The total area under the curve is the total brightness, and that's described by the Stefan Boltzmann law. That tells you the total light emitted at all wavelengths. All right. Jen, are you good? Kim? Can I erase? Let's try a quick problem and then we'll take a break. Okay. A tungsten filament in a typical Edison light bulb has a temperature of around 3,500 Kelvin. And that filament is giving off white light that you're using to illuminate your household lamp. I want to answer two questions. Question one, find the brightness of the filament. Question 2, find the peak wavelength emitted by the filament. Okay, question 1, which formula should I use?
Boltzmann formula.
The Stefan Boltzmann formula. Brightness is sigma t to the 4th. Rather than writing down that number every time, we just use the Greek letter sigma. It's kind of customary. But of course, sigma is 6 times 10 to the minus 8. The units are a little bit wild. Watts per meter squared per Kelvin to the 4th times the temperature, 3,500 Kelvin, excuse me. All right, I'm going to walk you through this calculation because I'm taking a guess that a lot of people don't know how to take a 4th power. So let's watch up here closely together on the calculator. I might need that Logitech thing. Oh, I hate this thing. Worried about autofocus issues, so. I don't care about this. Oh my God, is it making me sign in? Get rid of you. There we go. Okay. Okay, first we're going to do 6 exp negative 8. Now this is your power key, so watch, times 3,500, and we're going to raise to the power of x to the power of y 4, and then we hit equals. Did you guys get what I got? Jenna, how do you want to round that?
$9 million
What are the units?
watts over meter squared.
Very good. Here's an issue. Let me see if I can find it all here. I had another one of these around somewhere, but I couldn't find it. This is a 40-watt appliance bulb. Okay? And I will assert to you that this filament that you see in there, that will have a temperature of 3,500 Kelvin when I turn it on. I would like to turn it on for you, but all my extension cords are being used right now, and I fumble around for 10 minutes, and it's just not worth it. My question is, if this filament has a supposed brightness of 9 million watts per meter squared, then why is the light bulb only 40 watts? Anyone think they can answer that riddle? How can a 40-watt bulb be also producing 9 million watts per square meter?
This might be wildly wrong, but does it have something to do with It's not the distance, like the time, like how much it emits in a second or something.
No, no. It's about the thing that's glowing itself. The thing that's glowing itself is a little tungsten filament, right? When we talk about watts per square meter, we're talking about how many watts are glowing from a little square meter on the surface of the metal, right? But remember, class, a square meter is about the size of this dry erase board. If I had a sheet of tungsten that was 1 square meter and I heated it up to 3,500 Kelvin, then this square meter of hot tungsten would be giving off 9 million watts. The question you should ask yourself is, do you have a square meter of tungsten in that little filament? If I took a ball peen hammer and I smashed it out into a little square or rectangle, you would have a tiny, tiny fraction of a square meter, so tiny, in fact, that instead of emitting a brightness or a luminosity of 9 million watts, the luminosity was only 40 watts. Do you see what I mean? See, the issue is that brightness and luminosity measure different things. Brightness tells you how much light comes off a square patch, whereas luminosity is a property of the object itself. Let's see if you can understand the difference here. I don't know if I drove that point home carefully enough, but I'm gonna try. I really have to pause here. Take this thing. Let's imagine that the total luminosity of this brick of glowing metal is 100 watts. It also has a brightness, maybe it's a million watts per square meter or something. If I took a second identical glowing brick at the same temperature and I stacked it on top of the first one, would its luminosity change and would its brightness change?
Its brightness would stay the same, but the luminosity would increase.
You understand me perfectly, Jenna. In fact, the luminosity would double more or less because you'd have 2 glowing objects at the same temperature. Very good. The amount of light you get per square patch wouldn't change, but the total light output would change. Like 2 40-watt light bulbs gives you 80 watts, right, Jenna? Okay, good. Nice. Why don't we calculate the peak emission, then we'll take a break. So for answer 2, we're going to use Wein's law. $3 million. The units are nanometer kelvins divided by the temperature. Actually, I'll just replace the temperature with 3,500 Kelvin. What does that give me, class? Punch it up.
Would it be 857 nanometers?
Let's round it to 860. Very good. Hey, Paul G, can you tell me in what regime of the electromagnetic spectrum that's located?
That's probably going to be on the border of the visible spectrum and the infrared spectrum.
Yeah, it's kind of just over the border into the infrared. In fact, Paul G, if you look at that graph that I showed you earlier, just to kind of make a point out of this, that's what this curve is showing you here. This is similar to a tungsten filament. We just found that the peak wavelength is just past the red end of the spectrum, and it's actually into the infrared. In fact, one of the reasons why we've begun phasing out these old incandescent light bulbs, they produce a kind of nice warm yellow light, but the problem is this thing might cost you 40 watts of power, but most of the light that it's producing is being pumped out in the infrared, not in the visible portion of the spectrum. And in fact, you can feel that infrared light. If you've ever put your hand up next to a glowing light bulb and felt that little burning heat coming off of it, you're actually feeling, you're not feeling the air, you're feeling infrared photons coming off of that thing and heating up your skin like a piece of toast in a toaster. The reason why this light bulb is only 11 watts, but this light bulb is going to be way brighter than this one, is because this is not being powered by black body light. It's being powered by the law of emission. These new fangled light bulbs that they have blue, green, and red LEDs that are blended together to make white light. But because it's being powered by the law of emission, these light bulbs power all of their light entirely in the visible domain and not in the infrared. So first of all, they're not warm. They don't heat up your hand. And they can be way lower wattage because all of the wattage is going into the visible light. And that's why like a 20 watt LED has the same potency as a 100 watt incandescent bulb, because you're pumping all of the light into the visual domain where you want it. By the way, it's also cheaper for your electricity bill, so it saves you money. Better. I have to admit, I still kind of like the old incandescent light bulbs, just for aesthetic purposes, but they're very vulgar. All right. We've done it. We've spent another hour and a half learning about light. Let's have a think here. I think there's more than 5 of you, which is good. And I am feeling okay. So I'm going to try to do the homework with you live. Sound like a plan? Give me a little break though. Can you handle that? Just leave it, Jordan. I'll get it. Okay. It's 1:38 iPhone time. So 1:55 iPhone time. Actually, I think I finally synced up my computer clock. Yeah. 1:55, we'll do the homework, okay? And I believe it's homework 6, chapter 5 and 6. If you guys want to make this more efficient and get done faster, load up those questions on a screen and be ready to go, all right? I'll see you guys in a little bit. Okay, everyone, I'm ready to go if you are. Let's crank this out so we can get on with our St. Patrick's Day celebrations, whatever that form takes. What do we got, Ian?
Sorry, one sec. I thought I had it open, but I guess I didn't.
It's homework number 6, right?
I think so.
I think we have problems from chapter 5 and chapter 6.
Yeah.
If you guys can read me those numbers, that would be super helpful.
Yeah, that would be 56, 58, 59 in chapter 5, and then in chapter 6, 52 and 54.
All right, let's get busy. Let's start with chapter 5, number 56. Ian, if you want to kick us off, that'd be cool.
Yeah. Sorry, one of the things looks like it's the wrong questions. So 56 is right here. X-ray photon. What is the wavelength of an X-ray photon with energy level 10 keV? and it says parentheses 10,000 eV, and then what is its frequency? And then there's a parentheses that says 1 eV equals 1.60 times 10 to the negative 19th joules.
They're giving us the conversion factor from EV to joules, which we're going to need. All right, how do we want to start this? What do you think?
Sorry, one sec. I'm looking at my notes because I'm trying to see if I have this.
We've been given an energy for an X-ray photon.
Yeah.
X-ray photons are short wavelength and high energy, right?
This wouldn't have anything. This wouldn't have anything to do with Monday's class, would it?
Would have everything to do with, well, kind of, but more the class beforehand is where we learned all the formulas for this.
Right. Okay. So I'll look.
We did talk about the stuff on Monday, but we also talked about it 2 Wednesdays ago.
Why can't I find this? Oh, wait. I think I found it.
What's that?
Think I found what I'm looking for? I don't know. I'm sorry. My notes are all over the place. I need to organize them.
Yeah, I mean, I'm just seeing if you guys know anything or if you're just baby birds waiting for the food here.
Well, I have, this isn't really a formula, but I mean, wavelength. Nope. Yeah, I don't know if I have this written down.
Ian, you got to start writing stuff down because you've got this.
I thought I was, but I guess I missed something, but I don't know.
Because I think we had this problem before too, where you like wrote down some things, but not other things.
Well, before it was just an example that I didn't write down, but I don't.
But you
I don't
always,
know.
you want to write down, I think the lesson that we're taking away from this is, Ian, if I write it down, you
Oh,
write it down.
I think I found it.
Okay, what'd you find?
I found a formula that might work. So, but I'd have to switch it around. So I have C, which is speed of light, right, equals the lambda wavelength times F.
All right, that's one formula. Unfortunately, this formula does not contain energy, and that's the one thing we were given, so.
Yeah. Well, in that case, I guess we could say E photon equals H times C over lambda over wavelength.
All right, that's one version. There's another version too. What's the other version?
Energy of the photon is H times F.
Right. So let's say we want to find the wavelength first. Which do you think is the best formula to use?
Well, I guess since we don't have frequency either, it would be E equals H times C over wavelength.
Do you know how to solve that for wavelength?
Yeah, so you would multiply both sides by the wavelength, and then you get that to equal, I guess, H times C over E.
That's right. And the E flips down to the bottom, right?
Yeah.
Wavelength flips up to the top, E flips down to the bottom. Now what do I do?
You would plug in what we have. So, and we want that in EV rather than KEV, right? So that would be 10,000 EV on the bottom.
Hold on. My value for Planck's constant is 7 times 10 to the minus 34 joules times seconds. My value for the speed of light is 3 times 10 to the 8 meters per second. Those are all so-called MKS units. EV is not MKS.
Right, okay.
That's your first problem.
All right, so then we would want to convert that.
Let's do a tricky thing. We can do this sometimes when we're feeling frisky. We can do the conversion right inside the problem. So we have 10,000 EV. Let's multiply by a division bar. What are my units going to be?
Would it be joules per second?
What are you talking about here? Just two-dimensional analysis.
Yeah. Okay. Well, EV is on the bottom for sure.
Right. And what goes in the top? What do I want to convert it into?
I guess joules.
That's right. I don't know where that per second stuff is coming from.
Yeah.
but-
Sorry, I got a little bit flustered when I couldn't find stuff, so I started just saying things.
So, but remember, you don't need to look anything up. You just need to know how to do dimensional analysis. I want to get
Yeah.
rid of EV and I want to make joules, right?
Yep.
What's my conversion factor?
That would be 1 EV is equal to 1.6 times 10 to the negative 19th joules.
Tell me where to put the numbers because I don't trust you anymore.
Okay, 1.6 times 10 to the negative 19th is on the top with the joules,
Right.
and then 1 EV is 1 EV.
All right. So do this times this, divide by that, and tell me what you get. Ah.
I got, I guess you would round it to 1.3 times 10 to the negative 10th, and that would be in, that's joules, meters? No, nanometers, meters, but then we would turn it into nanometers.
Good. So that answer comes out in meters because joules and seconds cancel. But you're right. It would be a little bit classier to convert that to nanometers. So let's do that. What's the conversion from meters to nanometers?
1 times 10 to the negative 9th is the whoa, said that weird. 1 nanometer is equal to 1 times 10 to the negative 9th meters.
So what do you get if you divide that by 1 exp minus 9?
Let me do that. Or I guess that would just be 1.3 times 10 to the negative 1.
That's wacky.
No.
Could you,
Okay.
you don't need to put that in scientific notation.
Yeah, so that would be 0.13 nanometers.
Good. Classy. I like your moves. All right, what do we want to use to find the frequency?
That we could do energy of photon equals h times f, and then flip that around.
Okay, so F.
Equals h over e.
No. F
No.
stays on the top, H flips to the bottom. F is on the
Oh,
top.
yeah,
F
that would
is alone, right?
that would be easy. Yeah.
Because
Okay.
otherwise, look, if you flip the E down here, you have to flip the F to the bottom and you get 1 over frequency equals H.
Yeah.
over, right?
I did that weird. Yeah.
That would be weird. Okay. We didn't convert the E to joules, so we'll have to do it again. That's one of the annoying things about not converting the E into joules.
Yeah.
1 EV is 1.6 times 10 to the shit. I'm running out of space here. I'm going to do it like this. Write the number out and then do joules per EV. Okay, that's a cute trick. Divide it by 7 times 10 to the minus 34 joule seconds. Thank you. Cheers. I wish I could say this was Guinness, but it's just hot coffee.
Okay, I got my answer. I'm just trying to work out the units. So that would be joules on top. So it would be seconds. So that would be, you could round that to 2.3 times 10 to the 18th seconds.
False.
Okay.
Your units are bad.
Yeah, go figure.
Let's see. EV cancels with EV. Joules.
Oh, would it be? No, never mind. Keep going.
What's left?
Seconds, right?
False. You're doing something wrong.
Okay.
I need you to figure it out.
Yeah.
I can't explain it for you. I've already explained it before, but you didn't remember. So this time you've got to figure out what you did wrong.
All right. Oof.
Oh, I think I know.
Jenna.
It's 1/2
Right.
Oh, yeah.
Seconds are on the bottom, and that means something to everybody else, Ian. It might not mean anything to you, but it means something to us that seconds are on the bottom. In fact, that reminds me of another unit, doesn't it, Jenna? What's that other unit called?
That is called a hertz.
That's right. It's 2.3 times 10 to the 18 hertz. Remember, Ian, if seconds is the last man standing, it's kind of important whether it's on top or bottom.
Yeah.
You don't
Sorry.
have the right to flip that up to the top because it sounds better for you.
I think vacation threw me off.
That's okay.
Forgetting.
I think vacation threw me off. I think coming back to school was such a shock that I got sick. That's what happened. Right. All right, 1 down, 4 to go. Let's make our lives better. Can I erase, or do you need a moment?
I need a second. Sorry. I was working stuff out in my head. I didn't write.
Okay, all right. Let me know when you're good, Ian.
I'm just gonna take a screenshot of it and write it down in a second, so you can go.
Are you sure?
Yeah, because I have the whole board now, and I can write it down as when I have time, because I was doing stuff.
Okay, all right.
And if not, there's the recording.
True that. I just worry because sometimes you guys plan on doing things and then you forget about it. You know, that's my scare. But fine, I'll trust you. I'm going to erase.
All right.
Okay, Jenna, want to hit us with some 58? Chapter 5, 58.
It's called Thermal Radiation Laws. Part A, find the emitted power per square meter and wavelength of peak intensity for a 3000 Kelvin object that emits thermal radiation.
Okay, this is the kind of shit that just really goes right up my ass. I don't like this. They call it the power per square meter, which is particularly odious and offensive to me because power is a physical concept and square meter is a unit. This is the kind of student nonsense that is just unacceptable. What are the units of power? Oh, shit. Welcome to the slow lane. What are the units of power?
Energy over time, so joules per second.
Which is also known as, there's a better unit than joules per second. You're correct.
Is it watts?
Yeah, a watt.
In other words, what they were trying to say is find the watts per square meter. This still bothers me. This is still a lame way to talk. That's like saying, hey, how many dollars does that sandwich cost? You know, like, it's just a goofy thing to say. What are they actually asking us to find? What is the physical quantity they want us to find? What are you measuring when you measure in watts per square meter?
Is it brightness?
That's right. See, they could have said find the brightness or find the intensity. That would have been normal. But instead, they had to give us some gobbledygook just to try to confuse you to see if you could work it out. So we have two jobs here. One is to find the brightness. We also have to find the peak wavelength, lambda max. Damn, this sounds familiar. Did they give us a temperature, Jenna? I'm already lost in the sauce here.
3000 Kelvin.
All right. Let's start with the brightness. How are we going to do that?
We'll use Boltzmann law. So B equals the circle times temperature to the fourth.
Yeah. You could say Stefan Boltzmann constant times temperature to the fourth. That Greek letter is called sigma. Sigma. But I understand if you forgot that. Sigma has a constant, never changing value of 6 times 10 to the negative 8 watts per meter squared per Kelvin to the fourth. And then we're going to multiply that by 3000 Kelvin to the fourth power. Why don't you guys see if you can just punch that up nice and quick based on what we did in class today. Is that legible? That's supposed to be 3000. I'm getting jagged up in coffee here.
4.9 or 5 million
Perfect. What are the units?
watts.
Try again.
Oh, watts per meter squared.
Right.
So
The Kelvin to the fourth cancels with Kelvin to the fourth. 5 million watts per meter squared. I like your bold rounding moves, Jenna. A woman after my own heart. We also need to find the peak wavelength. You guys know what formula we want for that, of course, right?
Wein's.
Wein's law, if we want to say it like the Germans do. 3 million nanometer kelvins over the temperature. 3 million nanometer kelvins over 3000 Kelvin. What you got?
$1,000 nanometer.
What regime of the electromagnetic spectrum is that located in?
Infrared.
Very good. This is only part A, but the reason they chose this is that that's roughly the surface temperature of the star Beetlejuice. You guys will remember Beetlejuice. Open file location. It's actually up in our nighttime sky right now. I've been keeping track of it as I bumble around town at night. And notice that Beetlejuice is one of the cooler possible stars that we can have in the sky. And it's got this brilliant red color. Red stars are somewhat more rare than blue stars to see at night. They're not more rare in reality, but they're more rare for you to notice them on the sky. Since the surface temperature of this star is so cold, its Wein peak is actually over here in the infrared, but it pumps out a lot more red light than it does blue light. So its overall appearance to your eyes is somewhat red. In part B of this problem, they're going to ask us to do the same thing again, but this time for a different temperature. They're going to choose, I think it's what temperature is it, Jenna?
50,000 Kelvin.
All right. I'm feeling a little lazy here, so I'm going to erase this and write B. And I think one of the reasons they chose 50,000 Kelvin is this is one of the hottest types of stars that you could potentially find. So once again, I'm going to replace the temperature in the Stefan Boltzmann law with 50,000 Kelvin. And I will replace the temperature in Wein's law with 50,000 Kelvin. You guys will have to write it all out again, unfortunately, but I'm going to be a little bit lazy here, save some magic marker. So why don't you guys give me some numbers when you're ready to go? Yeah. Anyone got some numbers for me? Jenna, you do? Are you saying yes? Hit
Yep.
me.
So I got 3 times 10 to the negative third watts per meter squared.
No freaking way. You're raising 50,000 Kelvin to the 4th power. Last time you got 5 million watts per square meter, I would expect a 50,000 Kelvin object to be producing way more light. Anyone
Yeah.
else get a different number? Try punching that again, Jenna. You made an error.
I got 3.75 times 10 to the 11th power watts per meter squared.
What do you say we just round that up to 4?
Okay.
Just because the hell with it, right? That sounds better. 4 times 10 to the 11 is 400 billion watts per square meter. That's a lot of light output. Okay, Paul, you're on a roll. Did you get the peak wavelength?
I got 60 nanometers.
Paul, in what regime of the electromagnetic spectrum is 60 nanometer light found?
Would that be gamma ray?
No. Gamma ray is between 0.01 and negative infinity nanometers.
Ultraviolet?
Yeah. As an example of the kind of star that would look like this, consider the counterpart to Beetlejuice in the constellation of Orion. Consider the great blue star Rigel. Rigel is a blue supergiant. I don't know exactly what its temperature is, but this bright blue star probably pumps out more ultraviolet light than it does visible light. And as a result of that asymmetry, it appears quite blue. One of the reasons you're more likely to see blue stars than red stars, it's not because blue stars are more common, they're just super freaking bright. So when you're located on Earth and the stars are far away from you, there's lots more insanely bright blue stars that pop out than there are insanely bright red stars. The only reason Betelgeuse ends up being so bright is because its radius is so big. But that's a story for a different day. Okay, 2 down, 3 to go. Oh. I'm ready to erase. Does anyone need a second or going once, going twice? Gone.
I
Uh,
did part of the first part of that. I was just finishing writing it down when you started to erase the first answers.
Well, what the fuck? That's why I asked, can I erase? And I said going once, going twice,
No,
going.
no, no, not this past time. Like before when you filled in the 50,000.
Are you good or are you not good?
I'll probably be fine. I can just calculate it myself, but yeah.
Okay, look, I am trying to set a pace that works for you guys. I don't want to go too slow because we'll waste time. I don't want to go too fast because I'll lose you. I require feedback to know how to regulate, right, Ian?
I'm sorry. I was trying to.
I'm not really mad, I guess. I'm sorry myself. I wish that I had known you were still writing. Okay.
No, that's okay. I didn't want to slow you down.
Which part did you get lost in?
Nothing. I'll get it. I'll just do my own calculation. You'll probably be
Remember, there's only 4 of you sharing video with me right now, so I can give you some personalized attention. You're the only people talking to me, so we can talk to each other. So, all right, I'm sorry, Ian. Next time I'm gonna wait a little longer, I guess.
No, that was my fault because I tried to catch up on the first one. But yeah.
All right, I see what you did. Chapter 5, number 59. Okay. Kim, are you down to read that one for me?
Yep, that's fine. It's hotter sun. Suppose the surface temperature of the sun were about 12,000 Kelvin rather than 6,000 Kelvin.
Okay.
A,
Kim, I'm just going to make a point here. So actually, you know what? I'm going to use their numbers. So actually, no. The original temperature of our sun is 5,800 Kelvin. And they're asking what happens if the temperature goes to 12,000 Kelvin?
yes.
All right, and keep going. Sorry, I just wanted to get those numbers down.
Okay. A, how much more thermal radiation would the sun emit?
Okay. Why don't we just pause there?
Okay.
I'm going to try to show you guys a slick way to do this problem. But first, I need you to tell me what this formula is asking. I'm sorry, what this question is asking by telling me which formula we should be using here. Which formula tells you the quantity of thermal radiation emitted by a hot, dense solid?
So it would be the Boltzmann law.
The Stefan Boltzmann law, correct. So that's brightness is sigma times T to the 4th. Now listen, what they probably had in mind for you guys to do was to do it once for 12,000 Kelvin and another time for 6,000 Kelvin, get the 2 brightnesses and then take the ratio. But I want to demonstrate to you that if you do it algebraically first, you can save a lot of time. Let's in our minds divide the brightness at 12,000 Kelvin by the brightness of 6,000 Kelvin. And let's put in both formulas at once. On the top, we have sigma T to the 4th for 12,000 Kelvin. On the bottom, we have sigma T to the 4th for 6,000 Kelvin, where I've used the temperatures as little subscripts to keep track of what's going on. These are just labels to remind me what's what. You will notice the Stefan Boltzmann law appears twice and can be canceled out. And now I'm going to play some slick Rick maneuvering here. I'm going to factor out the 4th power. And you'll notice that it's just the ratio of the temperatures at 12K over 6K, all raised to the 4th power. This is kind of like a proportionality argument style. So in other words, what's my answer going to be? What is the ratio of temperatures?
It would be 2 to the 4th power.
Which is what, Kim?
Is 2. Okay, wait a minute. 2 Kelvin.
Huh? Feel free to use your X to the Y key if you don't know what 2 to the 4 is.
Hang on, sorry.
It's 2 times 2 times 2 times 2, but
16.
yeah. What is the meaning of 16?
Kelvin.
No. 16 Kelvin is like
16
almost at
Kelvin.
absolute 0. We took a ratio of brightnesses here.
Oh. Okay. Brightness.
Does anyone know what 16 means?
Is it the factor of how much more brighter one star is over the other?
Yeah. 16 times brighter sun. It means if the sun's temperature was twice as hot, we would actually be getting 16 times more radiation from the sun. Do you think that would be a pleasant planet to live on? Not unless you're a tardigrade, okay? And even then, I don't think the tardigrades would like it that much. 16 times is a lot more radiation. Imagine if you could make 16 times more money. That'd be cool.
Be nice.
Yeah, I'm saying that, Kim. I'll take that up with the management. All right, let's try part B. Ian, please let me know when you personally are ready to continue.
Yeah, I'm ready. Sorry. It was just that one problem. I got ambitious and thought I could do the whole first one before you finish part A of that one.
Okay. So you're totally comfortable, 100% comfortable with me erasing this?
Yes, 100%.
Everybody else comfortable with me erasing this? All right. Then I will erase. We have, oh, by the way, that's all part A, so we got to do part B now. Kim, what's part B ask?
Part B is what would happen to the sun's wavelength of peak emission?
To really understand this, I first want us to calculate the peak wave. We're not going to do this the way we did part A. This time we're actually going to calculate the peak wavelengths because it's an easy calculation, and I want you to see how the wavelength would shift. So now, today for the sun, lambda max is 3 million nanometer kelvins, and let's actually put in the surface temperature of the sun's photosphere, 5800 Kelvin. What's the peak wavelength emitted by the sun? Sorry, I'm kind of dying today. Wicked simple calculation. What'd you
So
get?
it would be 517, so round it to 500 nanometers.
All right, or we can probably use 2 sig figs, but
Okay.
we could do 500 too. You know what? Fine. Kim, I accept.
Okay.
Kim, what color is 500 nanometers?
It is.
Need a cheat sheet?
It is. Oh my God. Hang on. UV.
Nope.
No.
Look at my slide.
Oh, sorry. It's the visible spectrum.
What color?
Blue, light blue,
That's it.
indigo.
No, effing wait.
indigo,
This
okay.
is indigo. This is blue.
Okay.
500 is like green. 500 to 520 is green.
Okay.
500 is where green starts. Kim, did we just calculate that the sun is green?
Yeah.
Shit. If you give a kid a box of crayons and tell them to draw a picture of like outside, what color will they use for the sun?
Yellow.
Right. So why did we just calculate that the sun is green? I'm confused.
That's isn't it because the wavelength gets less stronger as you get closer to us?
I'm not buying any of that.
Okay.
A wavelength cannot be stronger or weaker. A wavelength can be longer or shorter. We've calculated that the wavelength, the peak intensity of the sun's light is 500 nanometers. What were you going to say, Ian?
Nothing. I just was trying to think because I know that the reason plants are green is because they reflect the green light from the sun, which I'm pretty sure it's like red and green light, but they absorb red, but that's not really relevant to anything. I was just trying to work out how that could factor into this.
Well, the whole thing with the chloroplasts reflecting green light, that's a biology thing. And you are correct what you said, but it doesn't really relate to the question. The question is, I just calculated that the maximum wavelength of light emitted by the sun is green, yet I know from playing with crayons that the sun is yellow. And I'm trying to understand how both of those things can be true.
I mean, is it the wavelength as it travels further, it gets wider between the crests?
No. Look, the peak wavelength doesn't tell you necessarily the color of an object. It tells you that the peak wavelength is the maximum wavelength. But the sun is still emitting lots of blue light and roughly equal amounts of red light. And then you mix it together with green light. And what do you get if you mix red, green, and blue?
White.
You get white. And that is the color of the sun. It's not yellow. You just think it's yellow because you're looking at it through the distorting atmosphere of Earth. I want to show you a picture of the sun as seen from the International Space Station. What color does the sun look in this photograph?
Very white.
It's the purest goddamn white you've ever seen in your life. It's almost a perfect blend of a little extra green plus gobs of red and blue. And the sun from space is just a brilliant white.
And you can kind of see the red, green, and blue in the.
That's an effect called a lens flare. That's an artifact because they're taking the photograph through the glass of a porthole, and the porthole is probably scattering and refracting light in complex ways.
Yeah.
You cannot, just like it's tough to see the individual pixels of red, green, blue on a computer screen. I see why you said that, Ian, but unfortunately that's not what's going on here. That's a lens flare effect of light hitting the glass. Why does the sun look yellow? Well, the atmosphere of Earth scatters blue light. And if you take white light with a little bit of extra green and you pass it through the atmosphere, the blue light gets scattered sideways. And as you remove blue from the spectrum, the sun ends up appearing yellow on the ground. In fact, it doesn't always appear yellow, does it? Think about a sunset. What color is the sun at sunset?
Orange.
Orangey red. And that's because you're looking through a longer column of atmosphere when you're looking sideways through the Earth, and you're scattering even more blue light out of the spectrum. So as you take the spectrum of the sun, if blue light is scattering this way and this way and this way, the sun itself will appear not just yellow anymore, but a kind of orangey red, right? That's a nice picture, actually. I might use that again. Let's see what would happen to the sun if we doubled its wavelength. That was a tangent. I shouldn't have done that, but I did it. So now let's go to 12,000.
$250 nanometers.
Yeah. If you double the temperature, you cut the peak wavelength in half. What color is that, Jenna?
Is it black?
No, it's not black. What regime? It's not in the visible spectrum, is what I was
It's in
hoping.
the ultraviolet.
Yeah,
Oh, yeah.
it's UV. There's a part C, is there not, Kim?
Yes, it says, do you think it would still be possible for life to exist on Earth? Explain.
Okay. Could you have life on Earth? Let's see. In part A, we learned there was 16 times more radiation. In part B, we learned that the light would shift from peaking in the green to having the sunlight peak in the ultraviolet. The UV light is what gives you a sunburn at the beach. Ian, do you think most organisms could survive if the sun was 16 times brighter and peaked in the ultraviolet?
Life as we know it could not exist like that.
Yeah, or it would only the most extreme of extremophiles. Whoa. Oh, shit. I think there's like some kind of Netflix sound. Yeah, I can just do that. That's really obnoxious of Netflix. Anyways, right. So 16 times, no. This is too much UV radiation. Maybe some underwater organisms could survive because the water would block that UV light a little bit more effectively. This is too much UV radiation for most land-based life. I'm not sure about the oceans because there are some organisms that can survive along deep sea trenches in basically boiling water at like 1200 degrees Celsius. So, and they would be protected from the ultraviolet light, which can, UV light actually breaks cell components apart, which is why it's so dangerous. But most land-based life couldn't survive this. Okay, 3 questions down, 2 to go. We're getting through this, guys. We're getting through it. Okay. Is everyone ready to proceed here? All right. I'm going to erase. I didn't quite get to the formulas for 52 and 54, but I'm just going to kind of walk you through them. And this will be your training on them. Nori, are you down to read chapter 652?
Did you say Nori?
I did.
Oh, I'm sorry. It like fuzzed out a little.
I figured I'd ask you to read next because I haven't asked you yet.
Okay. Question 52 is finding planets.
Okay.
Suppose you were looking at our own solar system from a distance of 10 light years. There's three parts to this question. So A is, what angular resolution would you need to see the sun and Jupiter as distinct points of light?
The angular resolution is basically how tiny an angle you can observe with your telescope. So I'm going to call that alpha. That's going to be the angle. And let's draw the picture here. You're looking from Earth. That's where you, the observer, is. And 10 light years away, you have the star, the sun. And they said the planet Jupiter, which is 5 astronomical units away. So here's the planet Jupiter. And I'm going to draw this triangle for you here. Why don't you guys take a second and draw that picture? Hey, help yourself to some minor survey and talking about it. Yeah. Okay. I'll be done like in 15, 20. All right, do you guys have that picture there? So the idea is you're looking through your telescope and you want to be able to see Jupiter and the star as distinct points of light. That means you're going to have to be able to see this angle here, alpha. This is very similar to what we did in chapter 2 with the small angle formula. We will call S the separation between the star and the planet, and D is the distance between you, the observer, and the planet. Now, in chapter 2, we had a version of the small angle formula that was cast for the angle in degrees. But in this case, we'd much rather have an angle that comes out in arc seconds, because the angle is going to be really small between the sun and the Earth. Let me introduce to you what's known as the small angle formula part 2. It's the same thing as the original small angle formula, but now we're basically doing a unit conversion so that the angle can be measured in the much tinier unit of arc seconds. And it has two versions. S is alpha times D over 206. Sorry, my handwriting is fucked today. One sec. Alpha times D over 206,265 arc seconds. That's one version. Or in today's lesson, we're going to want to solve it for the angular size. And when you do that, the angular size is 206,265 arc seconds times S divided by D. Now, I happen to know the distance between Jupiter and the sun is about 5 AU. Our distance is 10 light years away. And the issue with this formula is that S and D can be in any units you want because they're both distances, but they have to be the same units. Because I've done this problem before, I've discovered that it's much cleaner if we convert the 10 light years first into kilometers and then into astronomical units. So I'll kind of set that up for you nice and quick. So for the distance, we have 10 light years. And I'm going to do 2 division bars. The conversion here is light years on the bottom into kilometers. Since your class deals with the solar system, I really haven't bothered talking to you a lot about light years because we're not going to really need them because we don't leave our solar system. So I'm going to give you the conversion factor from light years to kilometers. 1 light year is 9.5 trillion kilometers. Then we're going to go from kilometers to AU. And you guys are supposed to know the conversion there, right?
It's 150 million AU to kilometers to 1 AU.
That's right. So that means 1 should go on the top and 150 million on the bottom. All right, punch that up for me and tell me what you get. Oh. I have house guests today, and they're learning a lot by secondhand education. What you got?
So would that be, let me see if I can round this. That is 600,000 AU.
Nice. I like your moves. So let's remember that 600,000 AU for 10 light years. That's why we really don't need light years in this class, because that would put you well outside the solar system, right?
Yeah.
Okay, so now, unfortunately, I like my drawing and stuff because it's cute, but I'm gonna have to erase this because I'm running out of board space. So Ian and friends, do you have all that? Take a moment here.
Yeah, I have that.
You sure now, right? All right. All right.
Yeah.
Fine, fine. So we have our S 5 AU and our distance at 600,000 AU. Okay, so for part A, for Jupiter, the angular resolution that you would need is 206.265 arc seconds times 5 AU divided by 600,000 AU. Punch them up.
Not sure how the units would work here, but I got
Two-dimensional analysis, Ian. You can handle that.
arc seconds into AU.
You've got arc seconds times AU divided by AU. So what does that leave you with?
Yeah, whoops.
Right.
Okay. All right, so that would be you could make that 1.7 arc seconds.
Correct. That's not just resolvable by a good telescope like Hubble Space Telescope, but even a small telescope could resolve that in theory. Anyways, what does it ask for part B, Nori? That's part A. Nori, are you with me?
Yeah.
Are you
I
down?
was just writing things down.
Oh, do you need a second to catch up? Take a second.
I don't think so. No, I'm okay.
All right, then give me part B.
Okay. So what angular resolution would you need to see the sun and Earth as distinct points of light?
Earth is even closer to the sun than Jupiter. So I'm going to superimpose Earth here. You guys know that Earth is only 1 AU from the sun. So in theory, this should be an even tinier angle. We're looking at our solar system like we're aliens from 10 light years away. And now Earth is only 1 AU away, and we're trying to calculate that even smaller angle. Here, the problem is the same. It's 206,265 arc seconds. The distance is the same. It's 10 light years, so we can use 60,000 AU, but we'll just change 5 AU to 1 AU, and that will speed things up for us. So the angular resolution is 206,265 arc seconds times 1 AU over 60,000 AU. Sorry, 600,000 AU.
I was about to ask about that. I thought I missed something.
Nope, that was just
It happens.
just the sickness talking. I'm dying right here. What'd you get?
I got 0.34 arc seconds.
How about just 0.3?
Okay.
0.3. So a third of an arc second. Box it up. That's a classy move. Is there a part C, Nori?
Yeah, there is.
All right, what's it say?
So how do the angular resolutions you found in parts A and B compare to the angular resolution of a Hubble Space Telescope? Comment on the challenge of making images, planets around other stars.
All right, so this is actually kind of an advanced question. It's a conceptual question, but I need to teach you some things for you to understand it, okay? The reason they're mentioning the Hubble Space Telescope is that the Hubble Space Telescope is the world's best telescope. But that's not because it's the world's biggest telescope. It's because it's the only optical telescope which sits above the atmosphere of Earth. And for reasons that I don't have time to get into, the atmosphere of Earth distorts the image that you're trying to observe, and it corrodes it so that you can only, the atmosphere of Earth limits your resolution to 1 to 3 arc seconds at best. The Hubble Space Telescope is only limited by the nature of optics and light itself. As it sits above the atmosphere of Earth, it's touching the vacuum of space, and there's no gas to distort that image of the planet and the star. Now, I'm quite sure that no one has read the book because no one does that kind of thing anymore. But if you were to read the book, you would discover that the limiting resolution of Hubble Space Telescope is 0.05 arc seconds or 50 milli-arc seconds. Let's write that down. I'm going to erase these two things here. So in part C, we want to write down that Hubble Space Telescope has a limiting angular resolution of 0.05 arc seconds. My question is, if I was looking at a solar system 10 light years away, would I be able to see Jupiter and the star as distinct points of light? Yes or no?
You would be able to.
Right, because this angle is smaller than the minimum angle you would need.
Yeah.
Would you be able to see Earth as separate points of light? So let's start by writing down, in theory, Hubble could resolve both of these planets from 10 light years away as 0.05 arc seconds is smaller than these angles. But this raises a question, Ian and friends. If Hubble can see planets 10 light years away, Believe it or not, there are stars closer to us than 10 light years, and they have planets around them, such as Alpha Centauri, 4 light years away, such as the star Sirius, 8.6 light years away, which probably has planets around it as well. So why don't I have any pictures of planets to show you outside of our solar system? I want to see the Ewoks dancing around on Endor. Why can't I see that?
Probably because it's so small, you're just getting like an impression of the light reflecting off it.
No, it's okay. It is true that the planets themselves would be too small to resolve, like forests and lakes and things.
Yeah.
But it's another issue altogether. And speaking of the star Sirius has a small white dwarf companion, and I want to show you a picture of it because it'll help you understand the problem. Let's look at the star Sirius, and I want to show you a photograph. This is one of a true resolved photograph of Sirius and its white dwarf star companion. Now, you can see that the star Sirius B can actually be resolved as a distinct point of light. But think about it. This itself is a star. Stars generate their own light in gobs of light. Can you imagine, Ian, if instead of trying to resolve a star, you were trying to resolve a planet like here, which only shines by reflected light? The issue is not one of angular resolution, it's an issue of brightness. In theory, you could resolve those planets, but the star is so much brighter than the neighboring planets that they get lost inside the glare of the star itself. So it's actually a brightness issue, why I don't have any planets of pictures of planets outside of our solar system to show you. So let's add a follow-up here, and we'll say, however, planets are so much dimmer than stars they're so much dimmer than stars, sorry about my handwriting, that their reflected light, because remember, you can only see a planet by light that bounces off of its surface, their reflected light would be lost in the much brighter glare from the star. Sorry about my handwriting. It gets kind of crappy at the bottom of the board here. All right, can you guys read that? Because I can say that one more time.
I can read it.
However, the planets are so much dimmer than stars that their reflected light would be lost in the much brighter glare from the star. And that's our fourth problem, and we've got one more to go, and then we can drink all the Guinness we want for St. Patrick's Day, okay? Which I'm seriously considering doing at this point. May I erase?
Don't worry, I got it.
Okay, okay. All right, here we go. Ian, it's back to you again. Chapter 654.
Sounds good. The size of radio telescopes. And that says, what is the diffraction limit of a 100 meter? This is 54, right? I'm doing that right?
It sounds correct to me.
Okay. Sorry, just had a second there. So what is the diffraction limit of a 100 meter radio telescope observing radio waves with a wavelength of 21 centimeters?
Okay.
Compare this. Oh, okay.
Yep, keep going.
Okay. Compare this to the diffraction limit of the Hubble Space Telescope for visible light. Use your results to explain why, to be useful, radio telescopes must be much larger than optical telescopes.
Okay. This is going to be a wicked simple problem in terms of the calculation, but it's a little more difficult to understand conceptually. First of all, just in case you don't know what the hell this is talking about, let me show you what a picture of a typical radio telescope looks like. The telescope I think they're referring to is the 100-meter Effelsberg Can I spell this? Effelsberg. I'm not spelling that right. Effelsberg radio. Let's see if Google will fix this for me. I happen to know that there is a 100, the Effelsberg 100-meter radio telescope. And radio telescopes kind of basically look like giant radar dishes, okay? They're designed to pick up radio waves from space. You can capture them from the ground, but radio telescopes are always totally insanely huge. The reason has to do with an obscure property of light known as diffraction. Diffraction causes a distortion and a bending of light that limits how tiny an angle a telescope or an eyeball can see. Like diffraction limits how tiny of an angle your eye can see things. It limits how tiny an angle a camera can see things. It limits how tiny an angle a telescope can see things. Too long, didn't read. Let me show you the formula, okay? The so-called diffraction limit for any optical device tells us that the minimum angle that you can see or detect is 250,000 arc seconds times the wavelength of observation, and here you plug in whether you're looking at visible light or infrared light or whatever, divided by d, which is the diameter or the aperture of your optical device. Now, if you're into photography and stuff, you know that the aperture is the dilated pupil through which you allow light to come through. Since astronomers want to collect as much light as possible, their aperture is usually the diameter of the objective lens. For instance, this aperture here would probably be a 3-inch. I bet this little crapper is a 3-inch. It's not even. It's like a 2.5-inch aperture. Okay. Okay. These have to be in the same units, or you won't get an angle in arc seconds. So let's draw a picture of our radio telescope just for fun and for art purposes. We'll have a big radio dish here, and we'll have a little feed horn. So that's what a radio telescope looks like. And we'll have a long wavelength radio photon, which is probably 21 centimeters, okay? We're going to have to convert that 21 centimeters into meters, which isn't too complicated. I'm going to do that part quick for you. 21 centimeters. Actually, you guys are supposed to know this stuff. How many centimeters in a meter? What?
100.
100. Okay, fine. So 1 meter to 100 centimeters. You made me nervous there for a second. 21 over 100 gives you 0.21 meters, right? And it's a 100-meter dish. So let's plug those values in and see what we get. Our alpha min is 250,000 times 0.21 meters over 100 meters. Punch them up.
Um, 525 arc seconds.
Let's just round it to
530
seconds. Hey, Ian, how many arc minutes is that?
Boy. So
I know you're good at dimensional analysis, right?
yeah, so that's going to be 530 arc seconds times, and then division bar and arc minutes on top and arc seconds on the bottom. And
Like your moves, kid?
It would be 1 on top with the arc minutes, and then 60 on the bottom, right?
In other words, divide that by 60. What do you get?
Yeah. I wasn't sure if you wanted me to do it out. Okay.
I mean, I did, and you did do it out. You did it in your head, which I accept.
So that is, if you round it, that could be 9.
9
arc minutes,
right?
Yeah.
But think about this, what that means, Ian. You guys are supposed to know the angular size of the moon. What's the angular size of the moon?
It's half arc minute,
Not a half an arc minute.
arc second.
Hell no.
It's half something. Sorry, I can't remember.
Half something, but the units matter, don't they?
Yes, they do. I can't remember. Let me check.
Does anyone else know, or are we leaving this all to Ian here? What's the angular size of the moon? This was probably a test question.
Half a degree.
Half a degree. How many arc minutes is half a degree?
60. No, sorry, 60 is 1. So that would be 30.
So in other words, the beam size of your radio telescope is 1/3 the diameter of the full moon at night. Let me paint a picture of what that means. If you took the Effelsberg radio telescope and you tried to take a picture of the moon at radio waves, this is what your picture would look like, okay? It would look 3 pixels tall and 3 pixels wide. That would probably be the shittiest picture of the moon ever taken in the history of astronomy. Your moon would be so grainy at this resolution, it would only be 3 pixels tall and 3 pixels wide. And this is for a 100-meter radio telescope. Radio telescopes have sucky angular resolution, right? Let's put that into context by comparing it to Hubble, which is what they suggested. If you compare a radio telescope, sorry, we're going to divide Hubble, no, we'll divide the radio telescope by the Hubble Space Telescope's resolution. That's 530 arc seconds divided by 0.05 arc seconds. What's our ratio turn out to be?
It's 10,600 times bigger.
It's 11,000 times. The point is, it's 11,000 times worse than Hubble. So the Effelsberg radio telescope is way bigger than the Hubble Space Telescope, but it's 10,000 times worse in terms of the image quality and the resolution. Why would I bother making such a device? What's the point?
I'm going to guess it picks up different things because it's for radio waves, right? Which
That's right.
Yeah.
If you look at space and radio waves, you can see things that you can't see in the optical. In particular, at 21 centimeters, it allows you to see the cold hydrogen gas in a galaxy, and that tells you where stars are forming. So you know your picture is going to be shit, but you take it anyways because you're desperate to learn about where the hydrogen gas is. For this reason, when I was growing up, the radio maps of galaxies that we would see, let's look at a radio map at 21 centimeters. They used to look horrible. They would be these big blobby images. This is what a galaxy would look like back in the day when you took a radio image of a galaxy. You could sort of see that there were spiral arms there, but it was so poor resolution that it was just garbage to look at. Today, we have new, better methods of combining multiple radio telescopes to make like a radio telescope the size of Earth. And that's how we can actually get some pretty good images in the radio today, but that's a story for a different day. There's one last part to this question, and then we can stop for the day. What was that last bit of question, Ian?
All right, 1 second. So we said we compared it to Hubble, and so use your results to explain why, to be useful, radio telescopes must be much larger than optical telescopes.
Okay, so I'm going to erase this part down here. Is that okay?
Yep, for me.
All right, so Ian, it seems like you're following me here. Let me see if you understand the answer to this, because it's kind of subtle. Why do I need to make radio telescopes so big if I want to make them useful?
I was thinking about this a second ago. Is it because, and this is why you can pick things up that are way further away, is because the radio waves are huge, right?
Right.
They like go have huge.
So if
wavelength.
radio waves are long, what does that do to your minimum angle?
Makes it very large.
Which is sucky, right?
Yeah.
So how do you compensate for that?
You make the diameter of the aperture much larger.
Which does what to your minimum angle?
Makes it smaller.
Which is what you want, right?
Yeah. Okay.
Since radio telescopes operate at long wavelengths, they have poor angular resolution, which in effect means a large angle. And the second sentence is, by increasing the diameter of the dish, which in this case, the aperture is the diameter of the dish, we lower the minimum resolvable angle. I think I spelled resolvable wrong there. I don't think there should be an E. The minimum resolvable angle and improve the image quality. You guys got that? All right, is everyone good?
I'm good.
Done it again. You've wasted another 3 hours learning about light and space with me. Like, comment, subscribe, and please, for the love of God, turn in your homework in your lab this week so I can grade them on Sunday. Sound good? Okay. You guys have a great weekend and a great St. Patrick's Day, whatever that means. It's kind of a fake holiday anyways. And I'll see you guys. I'll see you guys next Monday. Hopefully I'll be in better spirits then, okay?
Have a good week. Thank you.
Thank you.
All right. Take care, guys. Bye.